Hello, I will present to you our paper named Spatial Context Over Self-Attention Model for Multi-Organ Segmentation. We know that segmentation of organs or lesions from CT image has many clinical applications, for example, diagnostic interventions, treatment planning, treatment delivery, and etc. However, those segmentation were usually manually done by experienced doctor, which is time-consuming, tedious, and prone to human error. Traditional methods use atlas-based method. They are based registry two images. However, this may not adequately account for the anatomic variance among the patients. The second mainstream of a solution is based on deep learning-based method, especially UNet-based method. However, we are dealing with the 3D volumetric data. Now, there are two ways of doing this. One is slice by slice using 2D convolution, or we can use a block-wise 3D convolution. However, we know CT image by itself is a 3D, so there are more work that focus on segmenting organs from the whole image. This usually around two steps. The first is from a cost to fund level, where we need to train multiple convolution neural networks. The second is directly use whole volume input. However, they need very specific design architecture and with very specific input size and less effective to new dataset. In this work, we propose to incorporate the information in the whole 3D volumetric data into the 2D model to help guide the 2D model in a more scalable way. So we propose this new model called Spatial Context Over Self-Attention Model. It is new framework for combining 2D and 3D informations that takes the whole volume CT image as input. Second is, in order to better fuse the 3D context feature with 2D to guide our 2D segmentation, we propose a self-attention mechanism for that. Our model can scale to larger volume without concerning the GPU memory limitations that common 3D methods would face. So here is the whole architecture of our model. It consists mainly about three parts. First is 3D context decoder, where we take the whole volume CT image as input. We downsample it first, and then we use convolution and downsampling to get our 3D features. Second part is a unit-like shape architecture, where we take the one slice from 3D image, and then we take multiple downsamples and then upsamples to get our final segmentation. The main contribution is this module called multi-scale feature aggregation, where we take the 3D context features and the 2D slice features, and we use self-attention with multiple heads to generate our final features. And we do experiment on two datasets. One is MICAI 2015 and NEC. The second is an in-house abdomen multi-organ segmentation dataset, which contains 110 contrast-enhanced CT images with 11 organs. We use dye similarity coefficient and 95 Hausdorff distance for evaluating the performance of our model. Well, as we can see, with the full mechanism of our model, which is called SAA. On our in-house dataset, we see we achieved around 1.2 improvement around the previous state-of-the-art UNet model, and we show on the head and neck dataset, we also see considerable improvement and comparable to state-of-the-art results. So both of the two datasets show the model is effective, and we require less computational and GPU memory. So to conclude, we propose a spatial context over self-attention model for multi-organ segmentation. We use a self-attention mechanism to filter useful 3D context information from the large 3D whole volume CT image to help guide the segmentation of 2D slice. And this can help us largely reduce GPU memory concern that the whole volume-based 3D method we usually face, and we achieve the state-of-the-art performance on two multi-organ segmentation datasets to show the effectiveness of our proposed model. Thank you.